Before studying thermal equilibrium, we need to know what thermodynamics is. Thermodynamics is the study of exchange of heat and work between a system and its surroundings, and the resultant changes in the macroscopic variables of the said system. In thermodynamics, we deal with the macroscopic thermal properties of a system without knowing its internal structure. A thermodynamic system is an isolated body or a group of bodies with a well-defined boundary. It is important to identify the system, its surroundings, and the boundary that separates both of them. Some thermodynamic systems are as shown. Gas in a closed container is the system. The walls of the container act as the boundary. The environment acts as surroundings. Refrigerant is the system. The walls of the coil acts as the boundary. The compartment of the refrigerator acts as surroundings. The fuel inside an engine is the system. The walls of the engine are the boundary. Environment acts as surroundings. A thermodynamic system can exist in different states. The state of a thermodynamic system is identified by its macroscopic variables such as mass, pressure, volume, temperature, entropy, and enthalpy. For example, consider a given mass of gas at pressure P1, volume V1, and temperature T1. The state of a gas is identified by providing these values P1, V1, T1. If the gas is compressed, these values are changed to P2, V2, and T2. Then the new state is identified by P2, V2, T2. The state is said to be in equilibrium if there is no change in any of the macroscopic variables that distinguish the state with time. A system of gas in a container is said to be in equilibrium state if the pressure, volume, and temperature of the gas do not vary with time. The state of a system changes if the system exchanges heat with its surroundings, or when work is done by the system, or when work is done on the system. Whether a thermodynamic system can exchange heat energy with its surroundings or not depends on the nature of the boundary. An adiabatic wall does not allow any flow of heat through it, whereas a dithermic wall allows the flow of heat through it. That means an adiabatic wall acts like an insulating wall and a dithermic wall acts like a conducting wall. Consider a container with two chambers A and B separated by a partition. Take two gases in the two chambers, gas A and gas B. The state of a given mass of gas can be completely expressed by independent variables, pressure and volume. Let the initial state of the gas in container A be PA, VA, and that of the gas in container B be PB, VB, and the walls of the container and the partition between the chambers are adiabatic. As time passes, since the walls and the partition between the chambers are adiabatic, there will be no change in any of the macroscopic variables of either gas A or gas B. Let's retain the adiabatic wall as it is and replace the adiabatic partition with a diathermic material. Now, exchange of heat energy takes place between gas A and gas B, and as a result, there will be changes in their macroscopic variables. After sufficient time, they will settle at different equilibrium states, PA', VA' and PB', VB', and there will be no exchange of heat energy between them. We say that the two systems are in thermal equilibrium. Two systems, A and B, are said to be in thermal equilibrium when 1. They are in contact with each other or separated by a diathermic wall, and 2. The state of system A is in equilibrium with the state of system B. What will happen if we retain the adiabatic partition between the two chambers and replace the insulating walls with diathermic walls? After sufficient time, gas A and gas B will attain different equilibrium states. But as the walls are diathermic, gas A and gas B are in thermal equilibrium with the surroundings. If we replace the adiabatic partition between the two chambers with a diathermic partition, then there will be no flow of energy between gas A and gas B. Because when two systems, A and B, are individually in thermal equilibrium with a third system C, they are in thermal equilibrium with each other. This is known as the ZEROTH law of thermodynamics. Now, if we measure the temperature of all the three systems, we find all of them at the same temperature. This fact is used to define temperature. Temperature is the macroscopic variable that is equal for both systems when they are in thermal equilibrium. Consider two thermodynamic systems, say gas A and gas B, which are in two chambers of a thermally insulated wooden box and separated by a metallic partition. Let the initial temperatures of both gases be T1 and T2, with T1 greater than T2. We know that after sufficient time, they attain thermal equilibrium. Basing on this observation, temperature is defined as a thermodynamic variable that is equal for systems in thermal equilibrium. Systems at different temperatures and in thermal contact attain thermal equilibrium because heat flows from a hot system to a cold system. An important point to note about heat is that it is energy in transit. It exists as a flow only. A question like, how much heat does a sample of gas contain, has no meaning. In thermodynamics, the energy possessed by a system is internal energy, usually denoted by U. The internal energy of a system is the macroscopic thermodynamic variable that changes when it either emits or absorbs heat energy. For example, ice at 0 degrees Celsius converts to water at 0 degrees Celsius by absorbing heat energy. Though there is no change in the temperature, the internal energy of ice increases when it is converted to water. On the other hand, if water at 30 degrees Celsius is heated to water at 60 degrees Celsius, both the temperature and internal energy of water increases. At a microscopic level, the internal energy of a system is defined as the sum of kinetic energies of all its constituent molecules due to their translational, rotational, and vibrational motions, and the potential energies due to the interaction between these molecules. An important point to be noted is that the kinetic energy associated with the motion of the center of mass of the system does not influence its internal energy. Similarly, the internal energy does not include the potential energy due to the interaction of the system with its surroundings. For example, take a system of gas in a container placed at a certain height. If the container is dropped, the kinetic energy of the center of mass of the system increases, but there will be no change in the internal energy of the gas. The gravitational potential energy of the system is greater when it is at a certain height than when it is on the ground. But the internal energy of the system is the same in both cases. Let us now look at another example in our daily lives. We all are familiar with the fact that our hands become warmer when we rub them together. Though there is no external supply of heat energy to the hands, the work done due to the friction between the hands makes them warmer. This implies that the internal energy of the hands, considered in this case as a system, is increased by doing work. That means that by doing work, we can change the internal energy of a system. Let us now consider a mass of gas enclosed in an airtight container with a movable piston as a system. Now compress the gas by exerting an external force on the piston. This can be done by placing some weights on the piston of the container. We can observe rise in the temperature of the gas. When the gas is compressed, the external force due to the weights did some work, and as a result, the internal energy of the gas is increased. That means that when work is done on a system, its internal energy increases. Now, by removing the external force on the piston, if the gas is allowed to expand, the temperature of the gas decreases, indicating a reduction in its internal energy. Hence, when work is done by a system, its internal energy decreases. That means we have two different ways of changing the internal energy of a system. One by allowing the system to exchange heat with its surroundings, and the other by allowing it to do some work. In thermodynamics, heat and work are the two modes of energy transfer to a system. Heat and work are not state variables. They depend on the path through which the system is taken. For example, consider a given mass of gas at an initial state described by P1, V1, T1. Let us plot a pressure versus volume diagram for the gas and identify the initial state of the gas as A in the PV diagram. Let us take the gas to a new or final state described by P2, V2, T2, and identified by D in the PV diagram. We shall take the system from the initial state A to a final state D in two different ways. In the first method, place the container of gas on a hot reservoir maintained at a constant temperature T2 and allow the gas to expand at constant pressure. After sufficient time, the gas may be at a new state, identified by P1, V1-T2, and represented by point B in the PV graph. The curve AB represents the process of changing the state of the gas from P1, V1, T1 to P1, V1-T2. Now, keeping temperature constant, compress the gas by placing a weight on the piston to the final state P2, V2, T2. This change in the state from P1, V1-T2 to P2, V2, T2 is represented by a curve BD in the PV graph. In the second method, compress the gas by placing some weights on the piston and change the initial state of the gas P1, V1, T1 to a new state represented by P2, V-T1. In the PV graph, the new state is represented by C and the process by the curve AC. Now place the container on the hot reservoir maintained at a constant temperature T2 and allow the gas to expand at constant pressure to reach the final state P2, V2, T2. This process is shown by the curve CD in the PV graph. In this experiment, we have taken the system from its initial state P1, V1, T1 to a final state P2, V2, T2 by two different paths represented by ABD and ACD. Heat exchanged by the system in taking it from A to B and then from B to D is different from the heat exchanged in taking it from A to C and then from C to D. Even the work done by the system in taking it from A to D through ABD is different from the work done when taking it through ACD. In this aspect, the internal energy is different. Internal energy is a state variable. The internal energy of a system depends only on its state and is independent of the path through which it is taken. For example, in the experiment described earlier, let the internal energy of the system at its initial state P1, V1, T1 be U1 and the final state P2, V2, T2 be U2. Whether the system is taken through ABD or through ACD, the internal energy of the system in its final state remains U2 and is thus independent of the path followed. You have already learned that there are two different ways to transfer energy to a system. One is by heating the system, and the other is by doing some work on the system. The internal energy of the system may change during this exchange of energy with the surroundings. The relationship between the three important physical quantities, heat, internal energy, and work, is expressed by the first law of thermodynamics. The first law of thermodynamics states that the change in the internal energy of a system is equal to the heat absorbed by the system minus the work done by it on the surroundings. Consider a system of a given mass of gas in a container with a movable piston. When the gas is heated, let the heat energy absorbed by the gas be delta Q, and the work done by the gas while expanding be delta W. During this entire process, if the change in the internal energy of the gas is delta U, then, according to the first law of thermodynamics, delta U is equal to delta Q minus delta W, or delta Q is equal to delta U plus delta W. Note that the first law of thermodynamics is an expression of the general principle of conservation of energy. It is important to note that both delta Q and delta W can be positive or negative. If heat is absorbed by the system, then delta Q is positive, and if heat is emitted by the system, then delta Q is negative. Similarly, if work is done by the system, then delta W is positive, and if work is done on the system, then delta W is negative. What is the work done by the system? Let us derive an expression for the work done by considering gas in a container with a movable airtight piston of cross-sectional area A as a system. Let the pressure of the gas be P. Then, the force exerted by the gas on the piston F is equal to PA. If we assume that the force has pushed the piston through a small distance delta X, then the work done by the gas is denoted by delta W is equal to F into delta X, which is equal to PA into delta X or P into A delta X. But A delta X is the small change in the volume of the gas that can be denoted as delta V. Hence, the work done by the gas is denoted by delta W is equal to P into delta V. Let this be equation 1. In terms of differential calculus, equation 1 can be written as dW is equal to P dV. Let this be equation 2. Now, if we consider the expansion of the gas from its initial volume of V1 to a final volume of V2, then the total work done by the gas can be written as W is equal to integral dW between the limits V1 and V2. which is equal to integral P dV between the limits V1 and V2. Let this be equation 3. Though we have taken a gas in a regular shaped container to derive equation 3, this equation for work done by a thermodynamic system is applicable to solids and liquids as well. We can also apply this equation in phase changes. If a thermodynamic process is represented by a pressure P versus volume V graph, then the work done by the system can be graphically found. If during a process the volume of the system changes from V1 to V2, then the work done by the system is the area bound by the PV curve and the V-axis. For the given range of change in the volume of the system, let us apply the law to solve a problem. If 1 kilogram of ice at 0 degrees Celsius melts to water at 0 degrees Celsius at normal atmospheric pressure, what is the change in its internal energy? Given that the density of ice and water are 920 kilograms per cubic meter and 1000 kilograms per cubic meter respectively, and the latent heat of fusion for water is 335,080 joules per kilogram. Given mass of the ice m is equal to 1 kg, density of the ice d I is equal to 920 kg per meter cube. Density of the water dW is equal to 1000 kg per meter cube. Latent heat of fusion LF is equal to 335,080 joules per kilogram. On absorbing heat, the ice melts to water. If the heat absorbed by the ice is delta Q, then delta Q is equal to M into LF, which is equal to 335,080 joules. Let this be equation 1. If the volume of ice and water are represented by VI and VW, then VI is equal to M by DI, which is equal to 1 by 920, which is equal to 1.08 into 10 power minus 3 meter cube. Similarly, VW is equal to M by dW, which is equal to 10 power minus 3 meter cube. Therefore, the change in the volume delta V is equal to VW minus VI, which is equal to minus 0.08 into 10 power minus 3 meter cube. Let this be equation 2. As the melting of ice has taken place at atmospheric pressure P equal to 1.013 into 10 power 5 Pascal, the work done by the system in the process delta W is equal to P delta V, which, on substituting the values and simplifying, gives minus 8.104 joules. Let this be equation 3. Now we can apply the first law of thermodynamics to find the change in the internal energy of the ice. As per the first law of thermodynamics, delta U is equal to delta Q minus delta W. Substituting the values of delta Q and delta W from equations 1 and 3 and simplifying, we have the change in internal energy delta U is equal to 335,088.1 joules. Earlier, you studied that gases have two types of molar specific heat capacities. One is Cp, the molar specific heat capacity at constant pressure, and the other Cv, the molar specific heat capacity at constant volume. Now let us use the first law of thermodynamics to derive the relationship between Cp and Cv for an ideal gas. Consider a sample of mu moles of an ideal gas in a container with an airtight movable piston. On heating, the gas expands at constant pressure. Let the heat absorbed by the gas be delta Qp, where the subscript P indicates that the heat absorbed is at constant pressure, and the change in temperature is delta T. Then, delta Qp is equal to Cp into mu into delta T, or delta Qp by delta T is equal to mu into Cp. Let this be equation 1. For a change in temperature of delta T, if the change in the internal energy of the gas is delta U, then, as per the first law of thermodynamics, we have delta Qp is equal to delta U plus P delta V, or delta Qp by delta T is equal to delta U by delta T plus P into delta V by delta T. Let this be equation 2. But we know that for an ideal gas, PV is equal to mu RT. If we apply this law to the above process, we have P delta V equal to mu into R into delta T, or P into delta V by delta T is equal to mu into R. Let this be equation 3. On substituting the values from equations 1 and 3 in equation 2, we have mu Cp is equal to delta U by delta T plus mu R. Let this be equation 4. Now, as a second case, let the same gas be heated at a constant volume. If the heat absorbed by the gas is delta QV, where the suffix V indicates that the heat is absorbed at a constant volume, and the temperature change is delta T, then delta QV is equal to Cv into mu into delta T, or delta Qv by delta T is equal to mu into Cv. Let this be equation 5. But at constant volume, the work done by the gas delta W is equal to 0. According to the first law of thermodynamics, delta Q is equal to delta U plus delta W. As delta W is 0, we have delta QV is equal to delta U. Let this be equation 6. From equations 5 and 6, we get delta U by delta T is equal to mu into CV. Let this be equation 7. Note that in both processes, we have taken the change in the internal energy of the gas as delta U. This is because in both cases, the change in the temperature of the gas is delta T, and the change in the internal energy depends only on the change in the temperature of the gas. From equations 4 and 7, we have mu Cp is equal to mu Cv plus mu R, or Cp minus Cv is equal to R. This is the relationship between the two molar specific heat capacities of an ideal gas. The cylinders shown are oxygen cylinders. Usually, when filled with the gas, all these cylinders contain equal quantities of oxygen. But how can an empty cylinder be filled with exactly the same quantity of oxygen? The ideal gas equation is PV is equal to mu RT, where P is pressure, V is volume, T is temperature, and mu is the number of moles of the gas. R is the gas constant. Hence, if the pressure, volume, and temperature of the oxygen in different cylinders are the same, they must contain the same quantity of gas. Since the volume of all these cylinders is the same at a given constant temperature, if oxygen is filled to a certain pressure, all these cylinders will contain equal quantities of oxygen. If oxygen gas in a cylinder is treated as a system, we can reproduce the system by knowing the values of some of the properties of the gas, such as mass, pressure, volume, and temperature. The set of values of properties of a thermodynamic system, which are used to reproduce the system, is known as thermodynamic state, and the properties are also called variables. The state of the oxygen gas in a cylinder is expressed by providing values of its pressure, volume, and temperature. If the values are P, V, and T, then the state is represented by P, V, T. Now, consider the general case of a gas in a container and let the state of the gas be represented by PVT. If the variables that describe the state PVT have uniform values throughout the system and they do not change with time, the system is said to be in equilibrium state. If A, B, and C are 3 points in the system, and PA, PB, and Pc are the pressure of the gas at A, B and C, and Ta, Tb and Tc are the temperatures of the gas at A, B and C respectively, and if the state of the gas PVT is in equilibrium state, then Pa is equal to Pb is equal to Pc is equal to P, and Ta is equal to Tb is equal to Tc is equal to T. Not every state of a system is an equilibrium state. For example, if we suddenly pull the piston up, a vacuum is created above the gas, and the gas in the cylinder starts expanding against the vacuum. This is known as free expansion. During free expansion, the pressure and temperature of the system is not uniform throughout the system, and these values change with time. If P, Q and R are 3 points in the system, and at these points the pressures are Pp, PQ and PR, and the temperatures are Tp, Tq and Tr, then Pp is not equal to PQ, not equal to PR, and Tp is not equal to Tq, not equal to Tr. And these values at any point change with time. Hence, the state of the gas is not in equilibrium state. If the piston is completely removed, after some time, the gas is in mechanical and thermal equilibrium with its surroundings. If the pressure of the system is equal to the external pressure, then the system is said to be in mechanical equilibrium. And if the temperature of the system is equal to the temperature of the surroundings, then the system is said to be in thermal equilibrium with its surroundings. The variables that describe equilibrium state of a thermodynamic system are known as thermodynamic state variables. For example, if the pressure, volume and temperature of a given quantity of gas in a container is denoted by P1, V1 and T1, then its equilibrium state can be identified by P1, V1, T1, and P1, V1 and T1 are the state variables of this system. During any thermal process, if the equilibrium state of a system is changed, this is described by a change in the values of the state variables. If the gas in the container is compressed, and as a result if the pressure, the volume and temperature of the gas are changed from P1, V1, T1 to P2, V2 and T2 respectively, then the new equilibrium state is expressed by P2, V2, T2. As the name suggests, state variables of a system depend only on the state of the system, and they do not depend on the path through which the system is taken to attain this state. all the variables that describe an equilibrium state of a system may not be independent of each other. If pressure, volume, and temperature of a given sample of gas in a container describe its equilibrium state, then the volume of the gas depends on its pressure and temperature. The relationship between state variables is called an equation of state. For a sample of mu moles of an ideal gas in a container, the ideal gas equation PV is equal to mu RT is the equation of state. From this relation, we can understand that of the three variables P, V and T, only two are independent and the third one depends on these independent variables. In the case of real gases, the size of the molecule is not negligible compared to the average separation between them. And the intermolecular attraction is also not negligible. By taking the above two facts into consideration, van der Waals has derived an equation of state for a real gas, which is P plus A by V square, V minus B is equal to mu RT, where A and B are constants. The constant A is related to the average force of attraction between the molecules, and the constant B is related to the total volume of the molecules. The state variables discussed so far are of two types: extensive state variables and intensive state variables. A state variable that depends on the size of the system is called an extensive variable. For example, the volume of a system depends on its size and hence it is an extensive variable. Mass and internal energy are other examples of extensive variables. On the other hand, an intensive variable does not depend on the size of the system and has a uniform value in different subdivisions of the system. The pressure of the gas and temperature of the gas do not depend on the size of the system, and hence they are intensive variables. If a system of gas in a chamber, that is, in an equilibrium state, is divided into two equal parts, the variables that remain unchanged are intensive and variables whose values are halved are extensive. We can see that there will be no change in the pressure, density and temperature of the gas. Hence, pressure, density and temperature are intensive variables. On the other hand, mass, volume and internal energy are halved and hence these are extensive variables. In any thermodynamic equation, quantities on both sides of the equality symbol must be either extensive or intensive. For example, the quantities on both sides of the following equation are extensive. Delta Q is equal to delta U plus P delta V, where delta Q is the heat exchanged, delta U is the change in internal energy, P is the pressure, and delta V is the change in volume of a gaseous system. Here, as delta Q depends on the mass of the system, it is extensive, and though P is intensive, the product P delta V is. Let us first learn about the quasi-static process. Consider a wooden box with two chambers separated by a wooden partition. A sample of a gas is filled in the first chamber, and there is a vacuum in the second chamber. Let the equilibrium state of the gas in the first chamber be expressed as P1, V1, T1. If the partition is suddenly removed, the gas starts expanding freely against the vacuum. During this free expansion, the pressure and temperature of the gas are not uniform throughout. For example, if A, B, and C are three different locations within the box as shown, then the pressure and temperature at A, B, and C are different. Since the pressure and temperatures are not uniform throughout the system, the gas in free expansion is in a non-equilibrium state. Eventually, after sufficient time, the gas may settle at a final equilibrium state, P2, V2, T2. If we want to represent the process in a PV graph, we can only represent the initial and final states of the system as I, P1, V1, T1 and F, P2, V2, T2. We cannot identify the intermediate states as they are non-equilibrium states, and hence they do not have a well-defined pressure and temperature. Hence, in thermodynamics, it is always difficult to deal with systems in non-equilibrium states. As a consequence, a quasi-static process, an idealized process in which the system is in an equilibrium state at every stage, is defined. Let us understand what a quasi-static process is. Now, let us imagine that the vacuum chamber of the box we have considered earlier has a large number of similar partitions. We know that the initial state of the system is P1, V1, T1. If the first partition is removed, the gas quickly expands and there will be a small change in the pressure, volume, and temperature of the gas. Since the changes are very small, the system quickly attains a new equilibrium state. The new equilibrium state can be represented in a PV graph by point A as shown. If we slowly remove the partitions one after the other, at each stage, the system will quickly be in different equilibrium states. These different equilibrium states can be represented in a PV graph by points B, C, D, etc. When all the remaining partitions are also slowly removed one after the other, the gas passes through different equilibrium states and attains its final equilibrium state P2V2T2. The same thing can be graphically represented in a PV diagram as shown. The process we have shown is an idealized process in which the system is in equilibrium state at every stage. Such a process is called a quasi-static process. In principle, a quasi-static process is infinitely slow. As a result, the variables of the system change so slowly that at any intermediate stage, its state is an equilibrium state. This means that at every stage, the system is in thermal and mechanical equilibrium with its surroundings. In practice, a process that is sufficiently slow and with very small differences in the pressure and temperature between the system and its surroundings is a good approximation of an ideal quasi-static process. For example, if we want to take a sample of a gas in a container with a light movable piston, from an initial state P1T1 to a final state P2T2 through a quasi-static process, at every intermediate stage, the gas must be in thermal and mechanical equilibrium with its surroundings. To change the pressure of the gas from P1 to P2 through a quasi-static process, first, the external pressure needs to be changed by a small value, delta P. Then, allow the gas to equalize its pressure with that of the surroundings. Again, change the external pressure by a small value. And again, allow the gas to equalize its pressure with that of its surroundings. Continue the process slowly till the pressure of the system reaches P2. This way, we see that at every stage, the gas is in mechanical equilibrium with its surroundings. In the same way, to change the temperature from T1 to T2 through a quasi-static process, the temperature of the surrounding reservoir must be changed by a small quantity, delta T. By choosing reservoirs of progressively different temperatures, the temperature of each varying by a small quantity delta T, we can take the temperature of the system from T1 to T2. Usually, for our study of thermodynamics, we deal with quasi-static processes only. Now let us discuss isothermal process. If the temperature of a system is maintained constant throughout a thermodynamic process, it is called an isothermal process. A slow expansion or contraction of a gas in a container with dithermic walls is an example of an isothermal process. A dithermic wall is a wall that is capable of conducting heat. To maintain a constant temperature, the gas absorbs heat energy from the surroundings during expansion and releases heat to the surroundings during contraction. Since the internal energy of an ideal gas depends only on the absolute temperature of the gas, there will be no change in the internal energy of an ideal gas in any isothermal process. This means a change in internal energy delta U is equal to 0. Then, for an ideal gas in an isothermal process, the first law of thermodynamics, which is given by delta Q is equal to delta U plus delta W, reduces to delta Q is equal to delta W. In an isothermal process, during expansion, the gas absorbs heat from its surroundings and performs an equal amount of work on the surroundings. Similarly, during compression, work is done on the gas and an equal amount of heat is released into the surroundings. Now, let us find a mathematical expression for the work done by a system in an isothermal process. Consider mu moles of an ideal gas in a container that is at an initial state of P1, V1, T. The equation of state is denoted by the equation PV is equal to mu RT. Assume that the gas is isothermally taken to a final state P2V2T by expanding the gas. At an intermediate state, if the pressure of the gas is P and the change in its volume is delta V, then the work done by the gas during this process delta W is equal to P delta V. Then, the total work done by the gas during the entire process, in which the volume of the gas is changed from V1 to V2 W, is equal to integral V1 to V2 dW, or W is equal to integral V1 to V2 P dV. But P is equal to mu RT by V. Therefore, W is equal to integral V1 to V2 mu RT by V dV, which is equal to mu RT into integral V1 to V2 1 by V dV, which is equal to mu RT ln V2 by V1. Let this be equation 1. This is an expression for the work done by a system in an isothermal process. The PV graph of a system passing through a process at a fixed temperature is called an isotherm. In the graph shown, we have 4 isotherms representing the behavior of a given quantity of an ideal gas at 4 different temperatures. Another important thermodynamic process is the adiabatic process. If a system undergoes a process in which heat is neither extracted from it nor supplied to it, then the process is called an adiabatic process. This means that for an adiabatic process, delta Q is equal to 0. And the first law of thermodynamics reduces to delta U is equal to minus delta W. In an adiabatic process, the internal energy of a system increases if work is done on the system and decreases if work is done by the system. For example, in a 4-stroke engine, the system undergoes an adiabatic compression in a compression stroke. During this process, the work done on the system adiabatically increases its temperature. In a pass stroke, which is an example of adiabatic expansion, work is done by the system adiabatically, and as a result, there is a drop in its temperature. To restrict any exchange of heat with the surroundings, the system must be thermally insulated. This can be achieved if the system is placed in a container made of an insulating material like wood. Sometimes, a system passes through a process so quickly that there is not enough time for heat to be exchanged with the surroundings. Such processes are also called adiabatic processes. In the case of a compression stroke and pass stroke, the processes are adiabatic due to their speed. The PV curve shows an adiabatic process connecting two isotherms for an ideal gas. For an ideal gas in an adiabatic process, the pressure-volume relationship is expressed as PV to the power of gamma is a constant. Here, gamma is equal to Cp by Cv, where Cp is the specific heat or molar specific heat of the gas at a constant pressure, and Cv is the specific heat or molar specific heat of the gas at a constant volume. Let us find an expression for the work done by an ideal gas in an adiabatic process that takes it from an initial state P1V1T1 to a final state P2V2T2. The general expression for the work done is W is equal to integral V1 to V2 P dV. Let this be equation 1. But for an adiabatic process, PV to the power of gamma is a constant. Let the constant be K. This can also be written as P is equal to K divided by V to the power of gamma. Let this be equation 2. Substituting equation 2 in equation 1, we have W is equal to integral V1 to V2 K by V to the power of gamma dV, which is equal to K into V to the power of minus gamma plus 1 by minus gamma plus 1 from V1 to V2, which is equal to 1 by 1 minus gamma into K by V to the power of gamma minus 1 from V1 to V2 equal to 1 by 1 minus gamma into K by V2 to the power of gamma minus 1 minus K by V1 to the power of gamma minus 1. But P1V1 to the power of gamma is equal to P2V2 to the power of gamma is equal to K. Therefore, W is equal to 1 by 1 minus gamma into P2V2 to the power of gamma by V2 to the power of gamma minus 1 minus P1V1 to the power of gamma by V1 to the power of gamma minus 1, which is equal to P2V2 minus P1V1 by 1 minus gamma. Let this be equation 3. This is the expression for the work done by an ideal gas in an adiabatic process. We know that according to the ideal gas equation, P1V1 is equal to mu RT1 and P2V2 is equal to mu RT2. On substituting these equations in the above equation, we have W is equal to mu R into T2 minus T1 by 1 minus gamma. Equations 3 and 4 are the mathematical expressions for the work done by a system in an adiabatic process. Let us discuss another thermodynamic process known as isobaric process. If a thermodynamic process takes place at a constant pressure, it is called an isobaric process. Consider a sample of a gas in a container with a movable, frictionless, light piston. Expansion of the gas when heated is an example of an isobaric process. Since the piston is light, at any point in time during the expansion, the pressure of the gas in the container is equal to the atmospheric pressure. In this case, a part of the heat absorbed is used to increase the internal energy of the system, and the remaining heat is used to do work. The work done by a system in an isobaric process is W is equal to P delta V, which is equal to P into V2 minus V1. If the system is an ideal gas, then PV is equal to mu RT. Then the work done by an ideal gas in an isobaric process is W is equal to mu R into T2 minus T1. The PV curve for an isobaric process is a straight line parallel to the axis representing the volume of the system. Another important thermodynamic process is an isochoric process. In an isochoric process, the volume of the system remains constant. Heating a gas in a box of fixed volume is an example of an isochoric process. For an isochoric process, delta V is equal to 0. Therefore, the work done by a system in an isothermal process, delta W is equal to P delta V, which is equal to 0. The heat absorbed by the system is completely used to change its internal energy. This means that for an isochoric process, delta Q is equal to delta U. The PV curve for an isochoric process is a straight line parallel to the axis represented by pressure of the system. The adjacent graph shows all the 4 important processes we discussed in a PV diagram. We know that mechanical energy is required to run many machines. But major sources of energy, like fossil fuels, can generate heat energy. A device that converts heat energy into mechanical energy is called a heat engine. A steam engine, diesel engine, and a petrol engine are some examples of heat engines. In any heat engine, a small quantity of matter, usually called the working substance, acts as the system. For example, water is the working substance in the case of a steam engine, and a mixture of fuel and air is the working substance in the case of a petrol engine. The working substance undergoes a sequence of processes that finally leave it in the same state in which it started. Such a process is called a cyclic process. The schematic representation of a heat engine is as shown. In each cycle, the working substance passes through the following main processes. First, it absorbs heat from a hot reservoir maintained at a high temperature. Let the temperature of the hot reservoir be T1 and the heat absorbed by the system be Q1. After absorbing heat from the hot reservoir, the working substance does some work on the surroundings and converts part of the heat absorbed into mechanical energy. Let the work done by the system be W. At the end, the working substance rejects some heat to a cooled reservoir, maintained at a low temperature, say T2. Let the heat rejected to the cold reservoir be Q2. Again, the working substance goes through the same cycle. To get the required mechanical energy, the working substance goes through the same cycle repeatedly. In a cyclic process, the initial and final states of the system are the same, and hence there will be no change in its internal energy. That means delta U is equal to 0. But according to the first law of thermodynamics, we have delta Q is equal to delta U plus delta W. Therefore, for a cyclic process, delta Q is equal to delta W. As the heat absorbed and heat rejected by the system is Q1 and Q2 respectively, delta Q is equal to Q1 minus Q2. Since the work done by the system is W, we get Q1 minus Q2 is equal to W. Let this be equation 1. The efficiency of heat engine is defined as the ratio of the work done by the system to heat absorbed. Efficiency eta is equal to work done by heat absorbed, which is equal to W by Q1. But as per equation 1, W is equal to Q1 minus Q2. Therefore, eta is equal to Q1 minus Q2 by Q1, which is equal to 1 minus Q2 by Q1. Let this be equation 2. If Q2 is equal to 0, then the efficiency of the heat engine becomes 1 or 100%. This means, if we can construct a heat engine which converts the total heat it absorbed into work, then its efficiency is 100%. But in practice, it is not possible to construct a heat engine with 100% efficiency. This is not due to any technical aspect, but because of the second law of thermodynamics, which we will study in subsequent modules. There are two different types of heat engines. One type is the internal combustion heat engine. Diesel and petrol engines are examples of internal combustion engines, and the other type is the external combustion heat engine. The steam engine is an example of an external combustion engine. Let us discuss a 4-stroke petrol engine. This is also called an auto engine as it was first invented by Otto in 1876. The engine consists of a steel cylinder with a movable piston. The piston is connected externally to a crankshaft. There are two valves fixed at the top of the cylinder, I and E. Valve I is used to allow fuel into the cylinder, and valve E is used as an outlet of burnt gases. S is the spark plug used to produce electric sparks. The working of the petrol engine can be described in the following 4 steps. In the first step, a mixture of petrol vapor and air enters the cylinder through the inlet valve I. During this process, the piston moves down, and this is called the intake stroke. Now, both the valves I and E are closed, and the piston moves up. The upward motion of the piston compresses the mixture of fuel and air to a high pressure, resulting in an increase in the temperature of the mixture to about 500 degrees Celsius. This motion of the piston is called the compression stroke. At the end of the compression stroke, the spark plug produces a spark and ignites the fuel. Burning of the fuel generates a very high temperature and pressure and pushes the piston in the downward direction. This is known as a pass stroke, because this stroke provides a large amount of mechanical energy. Now, valve E is opened. The piston moves up and pushes the burnt gases out. This is called the exhaust stroke. In every cycle, the piston repeats all these 4 strokes. Hence, the engine is called a 4-stroke engine. Now, let us see how a steam engine works. It consists of a main cylinder with a movable piston. The piston is externally connected to a crankshaft, which in turn is connected to a flywheel. The top portion of the main cylinder has 2 ports called the front port and back port. In a chamber adjacent to the main cylinder, a valve is allowed to slide. The sliding valve is positioned in such a way that at any given time, both the ports are either in the open state or in the closed state. At the top of the chamber, there is a steam inlet and a steam outlet through which steam is allowed to enter or leave the cylinder respectively. The flow of steam into the main cylinder is controlled by the movement of the valve. Now, let us study the working of the steam engine. Since the required steam is generated in an external furnace, this is called an external combustion engine. Steam at a very high temperature is allowed to enter the chamber through the steam inlet. Let us start with the position where the sliding valve is in front of the front port and allows steam to enter the main cylinder through it. As the steam enters the main cylinder through the front port, it pushes the piston backwards. During its backward movement, the piston pushes the used steam out through the back port. Slowly, the valve starts moving backwards and the steam in the cylinder expands and pushes the piston further backwards. As the valve moves further backwards, the steam flows into the main cylinder through the back port, and it starts pushing the piston in the forward direction. The piston pushes the exhaust gas through the front port. Again, By moving the valve forward, we are back at the initial position. The repeated movement of the piston makes the flywheel rotate. Note that the movement of the sliding valve is controlled by a separate gear system. The movement of the valve is used to control the steam that enters the main cylinder and the speed with which the piston oscillates. Now let us understand the working of a refrigerator or a heat pump. The schematic representation of a refrigerator or a heat pump is as shown. A refrigerator is a device that takes heat from a cold reservoir, and after some external work is done on it, it releases some heat to a hot reservoir. Assume that the working substance receives heat energy Q1 from a cold reservoir at a temperature T1. And after W work is done on the system, it rejects heat energy of Q2 to a hot reservoir at a temperature T2. The coefficient of performance alpha of a refrigerator is defined as the ratio of heat taken from the cold reservoir to the work done. Alpha is equal to Q1 by W. But as per the law of conservation of energy, Q2 minus Q1 is equal to W. Therefore, alpha is equal to Q1 by Q2 minus Q1. Let us understand the working of a refrigerator. The working substance in a refrigerator is called a refrigerant, and in many refrigerators, ammonia is used as the refrigerant. The main parts of a refrigerator are the compressor, expansion valve, and heat exchanging pipes. The liquid refrigerant, while passing through the heat exchange pipes located inside, absorbs heat and evaporates. The vapor, which is at a low pressure, then enters the compressor. The compressor does some work on the vapor, and as a result, the pressure and temperature of the vapor increases substantially. The high-pressure hot vapor then passes through the exchange pipes located outside and releases heat energy to the surroundings. During the process, the hot vapor condenses to liquid. Then, the liquid refrigerant passes through the expansion valve, and due to sudden expansion, it cools further. In this way, the refrigerant absorbs heat from the cooler inside regions of the refrigerator and releases it to the hotter outside regions. Earlier, you learned that the efficiency of a heat engine eta is equal to 1 minus Q2 by Q1, where Q1 is the heat absorbed by the system from a hot reservoir, and Q2 is the heat released by the system to a cold reservoir. If Q2 is equal to 0, then the efficiency of the heat engine is 1 or 100%. Such a heat engine is called a perfect heat engine. This means a perfect heat engine can convert all the heat absorbed into work without any transfer of heat to the cold reservoir. Can a perfect heat engine be constructed? No. Every attempt to construct such a perfect heat engine has failed. In fact, the reason may not be technical. It may be of fundamental nature. For example, if an engine can convert all the heat to work, it need not take heat from a hot reservoir. But it could absorb heat from its surroundings and convert it into work. If that were possible, a car engine could have taken heat from the surroundings and run the vehicle without burning fuel. In fact, the process of converting heat completely into work is consistent with the first law of thermodynamics. But it seems that nature has put a constraint on such processes. There are many such processes that are valid according to the first law of thermodynamics, but which do not take place on their own. For example, if we rub our hands, they become warm. On the other hand, do both the hands absorb heat from their surroundings and rub each other on their own? Consider a metallic box with two chambers separated by a partition. One of the chambers is filled with some gas and the other chamber is empty. If the partition is lifted, we all know that the gas diffuses to the other chamber. Can the diffused gas molecules on their own move back and occupy the first chamber only? That will probably never happen. Some of these processes do not take place because nature does not permit them to. Hence, there must be a law of nature that decides whether a given process, allowed by the first law of thermodynamics, actually takes place or not. The second law of thermodynamics is the principle of nature, which disallows certain processes from taking place even though they are consistent with the first law of thermodynamics. There are many ways to state the second law of thermodynamics. One form of the second law of thermodynamics, which denies the possibility of a perfect heat engine, has been given by Kelvin and Planck. It states that no process whose sole result is to absorb heat from a reservoir and convert it completely into work is possible. There is another version of the second law of thermodynamics, which explains a fundamental limitation to the coefficient of performance of a refrigerator. Earlier, you learnt that the coefficient of performance of a refrigerator, alpha, is equal to Q1 by W, where Q1 is the heat extracted from the cold reservoir, and W is the work done on the system. If W is equal to 0, then the coefficient of performance is infinity. This means a refrigerator with a coefficient of performance equal to infinity can extract heat from a cold reservoir and release it to a hot reservoir without any external work on the system. Such a refrigerator is known as a perfect refrigerator. But the second law of thermodynamics places a restriction on this. The other form of the second law of thermodynamics, which restricts the possibility of a perfect refrigerator, is given by Clausius and states that no process is possible whose sole result is the transfer of heat from a colder object to a hotter object. This means we can't make a refrigerator function without any external work on the system. Both ways of stating the second law of thermodynamics are equivalent. Any one form of the law can be logically derived from any other form. Let us assume that the statement given by Clausius is wrong, and there exists a perfect refrigerator that absorbs Q1 heat from a cold reservoir at temperature T2 and releases the same to a hot reservoir at a temperature T1. Let there be a heat engine working between the same two temperatures T1 and T2. Let us also assume that this heat engine absorbs heat energy of Q1 plus Q2 from the hot reservoir, does some work W, and returns heat Q1 to the cold reservoir. If we take the combination of these two, the net effect is the absorption of heat Q2 from the hot reservoir, which is converted completely into work W. We can have a perfect heat engine. That means that if one form of the second law of thermodynamics is violated, and the other form is also violated. The first law of thermodynamics is a statement of the law of conservation of energy, according to which energy can neither be created nor destroyed. Whereas, the second law of thermodynamics restricts the availability of energy and the ways in which it can be used and converted. Consider a system taken from its initial state I to a final state F in a thermodynamic process. Let us represent the process in a PV diagram as shown. The process is called a reversible process. If the system and its surroundings can be brought back to the initial states without causing any change anywhere else in the universe. But many natural processes are not reversible. For example, when coal is burnt, it converts to ash and carbon dioxide and in the process releases some heat. Can the process be reversed and convert ash to coal again? We observe accumulation of dust everywhere in our houses. Can the accumulated dust on its own fly away and make the house clean? Not only the processes we have just discussed, but many other processes in nature are not reversible. In fact, we can conclude that irreversibility is not an exception but a rule of nature. Why is it so difficult to find a reversible process in nature? Let us consider a steady flow of liquid through a pipe of variable cross-sectional areas. As the liquid flows through the pipe, it may have different speeds at different points. Let the speed of the liquid at A be V1. When it moves from A to B, its speed increases, say from V1 to V2. The process is reversed and the speed of the liquid decreases from V2 to V1 as it moves from B to C. Hence, the process is almost reversed. The complete reversibility of this process is possible only if the liquid is non-viscous. This means the speed of the liquid is the same at A and C only if the liquid is non-viscous. However, in real life, this does not happen. Because of the dissipative effects due to friction, viscosity, etc., complete reversibility is not possible. As we can only minimize the effects of dissipative forces and cannot completely eliminate them, most processes in nature are irreversible. There is another cause for irreversibility that arises due to the system passing through non-equilibrium states. When the system is passing through non-equilibrium states, we cannot identify the intermediate states of the system precisely. As a result, we can't identify the correct path through which the system has passed, while changing from the initial state I to the final state F. Hence, reversibility of the process is very difficult. However, we have defined a quasi-static process as an ideal process that always passes through equilibrium states. Now, we can write the conditions for a process to be a reversible process. For a process to be reversible, it must be quasi-static. And there must be no dissipative effects. Like a quasi-static process, a reversible process is also an ideal one. For example, consider an ideal gas in a container with a frictionless movable piston. A quasi-static expansion or compression of this gas is an example of a reversible process. According to the second law of thermodynamics, we cannot construct a heat engine with 100% efficiency. So, what is the maximum efficiency of a heat engine? If a heat engine working between two temperatures, T1 and T2, passes through idealized reversible processes, then the heat engine achieves the highest efficiency possible. Much before the concepts of thermodynamics were established, Nicolas Léonard Sade-Carnot, a French physicist, proposed a hypothetical ideal heat engine that works with maximum possible efficiency. A hypothetical reversible heat engine operating between two temperatures is called a Carnot engine. To get the maximum possible efficiency, all the processes involved in the working of the Carnot engine operating between two temperatures must be reversible. Since all the processes are reversible, there will be no dissipative effects. We know that a process is reversible only when it is quasi-static. In a quasi-static process, the system will always be in thermal and mechanical equilibrium with its surroundings. There are two processes in which a heat engine exchanges heat with the surroundings. In one process, the heat engine absorbs heat from a hot reservoir at temperature T1. And in the other process, it releases heat to a cooled reservoir at temperature T2. Since the system must be in thermal equilibrium, these two processes need to be isothermal. There must be two more processes. In the first process, the temperature of the system changes from T1 to T2. And in the other process, the system is taken back from T2 to T1. Since there is no exchange of heat involved in these two processes, they must be adiabatic. The cycle of two isothermal and two adiabatic processes through which the working substance of a Carnot engine passes is known as the Carnot cycle. Let us now discuss the sequence of steps involved in each Carnot cycle. Consider mu moles of an ideal gas in a container with a movable, airtight, smooth, frictionless piston as the working substance. Let the walls of the container and the piston be made of thermally insulated material, and the bottom of the container be made of diathermic material. Assume that the initial state of the system is P1, V1, T1 and is identified by point A in the PV diagram. Note that the gas is in a compressed state because of some tiny weights on the piston. In the first step, place the container on a hot reservoir which is at a constant temperature T1, and slowly remove some of the tiny weights one after the other, and allow the gas to expand isothermally. During this expansion, let the state of the gas change to P2, V2, T1, which is identified by point B in the PV diagram. Let the heat absorbed by the gas be QAB and the work done by the gas be WAB. For an isothermal process, there is no change in the temperature of the system, and hence the change in the internal energy is zero. Therefore, the heat absorbed by the system is equal to the work done by it. Therefore, for an isothermal process, the work done by the system WAB is equal to mu R T1 ln V2 by V1. Let this be equation 1. In the next step, the container is kept on an adiabatic platform. Now, by removing some more tiny weights, one by one, allow the gas to expand. Since the gas is surrounded by adiabatic material, there can be no exchange of heat between the system and its surroundings, and hence the expansion is an adiabatic expansion. Let us assume that this adiabatic expansion has taken the system from B P2 V2 T1 to C P3 V3 T2, and that this is represented by the BC curve in the PV diagram. For an adiabatic process, heat absorbed QBC is equal to 0, and the work done WBC is equal to mu R into T1 minus T2 by gamma minus 1. Let this be equation 2. Since for an adiabatic process, TV to the power of gamma minus 1 is constant, we can write T1 V2 to the power of gamma minus 1 is equal to T2 V3 to the power of gamma minus 1. Let this be equation 3. In the next step, let us place the container on a cold reservoir, which is at temperature T2. By placing back some of the tiny weights on the piston, allow the gas to compress isothermally. In this process, the system releases heat to the cold reservoir. Assume that during the process, the state of the system is taken from C P3V3T2 to D P4V4T2. Let the heat given out by the system to the cold reservoir be QCT, and the work done on the system be WCT. Since the process is isothermal, QCD is equal to WCT, which is equal to mu RT2 ln V3 by V4. Let this be equation 4. In the final step, place the container on an adiabatic platform once again and compress the gas by adding small weights one by one. This adiabatic compression has taken the state of the gas from dP4V4T2 to AP1V1T1. The work done on the system, WdA, is equal to mu R into T1 minus T2 by gamma minus 1. Let this be equation 5. As the process is adiabatic, we can write T2V4 to the power of gamma minus 1 is equal to T1V1 to the power of gamma minus 1. Let this be equation 6. In one complete cycle, the work done by the gas W is equal to WAB plus WBC minus WCD minus WDA. Note that we have taken the negative sign for WCD and WDA as the work is done on the system during the compression. On substituting the values from equations 1, 2, 4 and 5, we get W is equal to mu RT1 into ln of V2 by V1 plus mu R into T1 minus T2 by gamma minus 1 minus mu RT2 into ln of V3 by V4 minus mu R into T1 minus T2 by gamma minus 1. On simplification, we get W is equal to mu RT1 into ln of V2 by V1 minus mu RT2 into ln of V3 by V4. Let this be equation 7. We know that the efficiency of the heat engine, eta, is equal to the ratio of the work done by the system to the heat absorbed by the system. The total work done is W, and the total heat absorbed is QAB. Note that heat is absorbed only during the process AB. In processes BC and DA, no heat is exchanged since they are adiabatic. And in process CD, heat is released. Hence, these three processes are not considered. Therefore, efficiency is equal to W by QAB. Substituting the values for W and QAB from equations 7 and 1, and on further simplification, we have eta is equal to 1 minus T2 by T1 into ln of V3 divided by V4 by ln of V2 by V1. Let this be equation 8. Equation 3 can be rewritten as V2 by V3 is equal to T2 by T1 to the power of 1 by gamma minus 1. Let this be equation 9. Similarly, equation 6 can be rewritten as V1 by V4 is equal to T2 by T1 to the power of 1 by gamma minus 1. Let this be equation 10. From equations 9 and 10, we have V3 by V4 is equal to V2 by V1. Let this be equation 11. From equations 8 and 11, we get eta is equal to 1 minus T2 by T1. Let this be equation 12. Hence, the efficiency of the Carnot engine eta is equal to 1 minus T2 by T1. We know that the Carnot cycle is a reversible cycle. Every process of the cycle is a reversible process. If each step of the Carnot cycle is reversed, we get a reversible refrigerator that receives QCD heat from a cold reservoir at a temperature of T2, and after work W is done on the system, it releases heat of QAB to the hot reservoir at a temperature T1. Let us now compare the efficiencies of two heat engines working between the same temperatures T1 and T2. One of the engines is an irreversible engine I, with an efficiency eta I, and the other engine is a reversible Carnot engine R, with an efficiency eta R. Let us start with the assumption that the efficiency of the irreversible engine is greater than the efficiency of the Carnot engine. This means eta I is greater than eta R. Let this be expression 1. If eta I is greater than eta R, then the work done by the engine I must be greater than the work done by the engine R. If Wi is the work done by the engine I, and Wr is the work done by the engine R, then Wi is greater than Wr. Let us call this expression 2. Now, let us couple both the engines, such that the irreversible engine I works as a heat engine, and the Carnot engine R works as a refrigerator. Since the Carnot engine is working as a refrigerator, Wr is the work done on the system. Let us assume that the heat engine receives heat Q1 from the hot reservoir and returns some heat Q1 minus Wi to the cold reservoir. Let us also assume that the engine R, which is working as a refrigerator, absorbs heat Q2 from the cold reservoir and returns heat Q1 to the hot reservoir. Then the work done on the engine R, Wr, must be equal to Q1 minus Q2. This also implies that Q2 is equal to Q1 minus Wr. But as per expression 2, we know that Wi is greater than Wr. Then we can conclude that Q1 minus Wi is less than Q1 minus Wr. But Q1 minus Wi is the heat returned to the cold reservoir by the engine I. and Q1 minus WR is the heat received by the refrigerator. Substituting the value of Q2 in this expression, we get Q1 minus WI is less than Q2. Since Q2 is greater than Q1 minus WI, the net heat taken from the cold reservoir is Q2 minus of Q1 minus WI. On substituting the values of Q2 and on further simplification, the net heat taken out of the cold reservoir is equal to WI minus WR. Note that the coupled system has received Q1 heat from the hot reservoir and has returned the same heat to the hot reservoir. This means the coupled system is able to extract net heat from the cold reservoir and convert it completely into work. This is a violation of the second law of thermodynamics. This means our earlier assumption that eta I is greater than eta R, or the irreversible engine is more efficient than the reversible Carnot engine, is wrong. This conclusion leads us to Carnot's theorem. It states that working between a given set of temperatures, no engine can have an efficiency greater than that of the Carnot engine. It also states that the efficiency of the Carnot engine is independent of the nature of the working substance. Though we use the ideal gas equation while deriving equation 12, it must be true for any working substance. If we compare equation 12 with the equation eta is equal to 1 minus Q2 by Q1, we get Q2 by Q1 is equal to T2 by T1. Note that this relationship Q2 by Q1 is equal to T2 by T1 is a universal relationship and is independent of the nature of the system.